Hello, everybody, and welcome to another wonderful day of chemistry. So, today we're going to be talking about that feature of chemistry that's often imitated, rarely replicated, the periodic table. It is one of the more useful tools we have as chemists. So, the origin of the table was essentially as a part of an effort to explain the behavior and especially the chemical reactivity of certain chemical elements. Because certain chemical elements tend to have similar reactivities, but nobody was quite sure how that could be turned into a predictive relationship. So in step Mendeleev, who ended up proposing one of the most enduring of these descriptions of chemical reactivity, which was the periodic table. So in its primitive form, what he did was he listed out all of the chemical elements known at that point according to atomic masses. And then he noticed that if you did so in certain regular repeating fashions, you would find certain patterns of reactivity. And these patterns, which we now call columns, essentially will have similar behavior. And he essentially phrased this as when chemical elements are arranged in order of increasing relative masses, certain sets of properties reoccur periodically. And thus it became the periodic table. The periodic portion is because as these elements go through rotation, you start seeing certain reactivities or properties keeping on reappearing. So as a result, it's these vertical groups that really end up defining so much of the periodic properties. However, it is worth noting that when he did this, Mendeleev, first of all, didn't even have atomic numbers to rely on, but he didn't have all of the elements at that point. There was often big gaps in his periodic table. And so one of the really impressive parts is that he predicted certain elements that were missing, that were later found. And so, in the intervening 150 years, we've managed to construct quite a complete periodic table, which now includes over 100 elements, including some like technetium over here at 43, which doesn't even occur naturally. This one wasn't discovered until experiments in radioactivity were able to make it synthetically. So again, it's been quite a successful little feature. And so what we often end up doing is taking this bigger periodic table and we subdivide it based on both physical and chemical properties. And most of these features do end up occurring along these repeating groups. So we're going to be looking into several of these major ones and kind of breaking it down. So don't worry if you're overwhelmed right now. We're going to start with some kind of gross patterns of the periodic table. So one of the simplest divisions is in between the metals, the nonmetals, and those that don't really belong in either category, the metalloids. So in kind of the grossest fashion, we can break the periodic table into metals over here in the lower left and nonmetals over here in the upper right. So when we're talking about metals, one of the most of these tend to possess certain reliable phenomena. First of all of them, with the lone exception of mercury, are solids, no liquids or gases at room temp. They all tend to be fairly malleable and ductile, which means you can tend to bend them fairly readily when they're in their pure elemental phase. They also tend to be fairly shiny. They all are very good conductors, meaning I can run an electrical current through it. And not too surprisingly, one of the reasons they are good conductors is they're all fairly vulnerable to losing electrons, which means most of them can tend to make pretty good cations because they can lose those electrons to get their positive charge. In contrast, we have the elements on the upper right side of the periodic table, which we call nonmetals. So these tend to exist over a huge array of phases. So they can be solids like carbon or phosphorus. They can be liquids like bromine, or they can be gases like fluorine, chlorine, good old mustard gas, iodine, which can actually range over, um, which can range from solids at essentially room temperatures up to essentially below the point of boiling water, go to a gas. And you'll often find it in both solid and gaseous form at room temp. Uh, Other things that tend to feature is that they tend to be very poor conductors. They carry an electronic charge fairly poorly. And one of the reasons why is that while metals tend to lose electrons during reactions, allowing for a transit of electrons through, say, a wire, in contrast, the nonmetals tend to like to collect electrons. So they tend to gain electrons, meaning they transfer um, electricity very poorly. And then we have this awkward phase of the metalloids. And essentially, these are everybody who's adjacent to this metal nonmetal feature, whether it's going from boron and aluminum to tellurium and polonium. These all occur as solids under room temperature, and they tend to have very controllable conductivity and fairly variable reactivity. So a good feature of that controllable conductivity is silicon. Silicon is naturally a conductor, or an insulator, but if you put it in the right circumstances, it can become a conductor. And this is the reason why computer chips tend to rely on silica, because you can by varying the conditions at which it carries electricity, you can essentially do those turning bits on and off, as in, does it communicate with the rest of the system? And it's this metalloid behavior that really has made the silicon revolution possible. All right, so these are kind of the big overarching groups of the periodic table. Let's go ahead and break this down a little bit more systematically by looking at specific groups. So one of the first ones is, well, group 1, the group on the further left side of the periodic table. We're going to ignore hydrogen for now because hydrogen obeys its own rules, as we'll see later. These are called the alkali metals, and they tend to have a very consistent set of properties. They're all very shiny, and as you see here with lithium, they're very soft, as in you can often cut these with a butter knife. And one of the more impressive features is when they're in their elemental phase, they can produce hydrogen gas and heat when they are exposed to water. Guess what happens when you have hydrogen gas and heat all in the same container? Yep, they're known for catching water on fire, because what ends up happening is you throw in the metal and it generates the hydrogen and enough heat to make it combust with oxygen. And thus, you get fire on top of water. And this is lithium, and the fire tends to be more pronounced as you work your way down the periodic table. Now, there's a reason why we typically don't think of sodium as catching fire when I put it in water. And that's because most of the time we're not dealing with the elemental form of these metals. Instead, we're often dealing with the cationic form, because most of the time they're found dissolved in water as an ion, whether it be lithium, sodium, potassium being the dominant features. You can even suspend them in matrices of other materials. So that's what happens with lithium ion batteries, is you have lithium in a mixture of other metals and gels, and the lithium can move backwards and forwards, making one of the major features of a lithium ion battery, because the lithium we're working with is ionic, not metallic. And that's a very important distinguishing feature, which tends to carry on in group 2, the alkali earth metals. So this always confused me when I was a student. Alkali metals are group 1, earth group 2. One word versus 2 words, group 1 versus group 2. That can kind of help keep it straight. A good way to think about alkali earth metals is they're the poor imitation versions of the alkali metals. They're also fairly soft, fairly silvery, fairly soft, and fairly reactive, but not quite as much as the alkali metals. They also will produce hydrogen gas and heat when exposed to water, but at a much slower rate. And as a result, uh, they're less known for essentially catching flame to water, and you're typically not going to see somebody like putting magnesium in water and watching the flames come out. However, that said, uh, you can actually burn the metals when you expose to flame. So a common example of that is if you've ever heard of magnesium wire. This is often what's used to essentially light fireworks. If you see a nice metal wire coming out of a firework, you essentially hold the flame to the wire, it catches fire, and then goes into the firework. Often what you're dealing with is magnesium wire or metallic magnesium. However, just like the alkali metals, you typically tend to find these as cations. The bigger difference is while the alkali metals lose one electron, the alkali earth metals, being second period, will lose two electrons. And we'll talk about why a little bit more later. Now let's go ahead and jump on over to the other side of the periodic table, over to group 7. So this is the second to the last column of the periodic table. So big features of group 7 is that it can form solids, liquids, and gases, and it's the only group that can do so. For example, iodine, as I previously said, is naturally a solid, bromine is a liquid, and chlorine, well, it makes mustard gas. And again, these are typically formed, especially in the gaseous state, as diatomic species. So chlorine gas is Cl2, bromine liquid and gas is Br2, and iodine is I2. They tend to be highly reactive when exposed to alkali earth metals, and one of the reasons why is because the halogens like making anions, while as the alkali and alkali earth metals like making cations. So in other words, halogens love mugging the alkali and alkali earth metals for their electrons. And this brings us to the last column of the periodic table, the noble gases. We're going to ignore helium, but it's often included. And they essentially occupy group 8. So these always form very non-reactive monatomic gases. You essentially really have to work hard in order to make a noble gas form a molecular compound. They almost always exist on their own. You are most typically familiar with thinking of noble gases in things like neon lights. Also things like helium in balloons, and because they're very unreactive, scientists love using them for inert atmosphere. Because if we want to work in a system where they don't react, where no chemical reactions occur, noble gases are for you. And again, one of the very cool features of these noble gases is as they don't react, we can often expose them to conditions that most other elements don't allow, such as in these neon lights, where we can bring them to very high temperatures and run large charges through them to generate quite beautiful colors that we'll be talking about a little bit later this semester. Now, one of the other things that is worth noting is that these are just 4 of the more pronounced subdivisions of the periodic table. There's also a lot of other ones that you can make, and we'll play around with some of these as we go through the semester. So another big feature is what's called the main group, and that's essentially groups 3 through 7 here. They tend to have very nice, consistent behavior, and there's a reason why biology likes using the most abundant form of them, mostly carbon, nitrogen, oxygen, sulfur, and phosphorus in a lot of compounds, both because of a very flexible set of reactivity and their abundance. We also have the transition metals, which essentially form this awkward gap in the periodic table. The last set that is often worth noting is the lanthanides and the actinides. So these essentially are those 2 rows that are always sitting at the bottom of the periodic, below the periodic table. And one of the reasons why, and we'll see this later, is you can actually insert them in between the alkali earth metals and transition metals. And they essentially have very unique sets of reactivities, and that's partially because you'll see by their high molecular weights, they are quite heavy and can do some things that most other systems can't. But they tend to be fairly rare and fairly radioactive. So one of the things that's going to be worth keeping in mind as we move forward through the year is that if you can is that understanding a lot of these groupings of the periodic table can be really useful in understanding chemical reactivity. And I'm going to try and mention these various periodic trends as we move forward through the semester. However, next time we have to return to that unfortunate topic of math as we try and figure out how we can count our atoms to make use of, well, figuring out how many atoms are going to be in a typical sample. Until then, take care.